Okay. Ultimately, our example is to take the function g of x equals 6x to the fourth minus 7x cubed, etc. We are trying to ultimately determine all the zeros and write the factorization for it. In other words, break it up into potentially four factors since it's an x to the fourth. When we do this, we want to kind of narrow it down. I don't know how to factor a 6x to the fourth very easily. I don't see anything in common all the way through or anything like that that's going to help me. So I look at the possible rational zeros first. And the possible rational zeros, the rational roots theorem says that possible rational zeros would be P over Q, where P would be factors of the constant, and Q would be factors of the leading coefficient. So this is our P, and this is our Q term. So my factors of P would be all the numbers, positive and negative, that go into 12. So there's a bunch of them. In fact, it's so many that I'm going to make my font a little smaller, and I'm going to say positive negative 12, positive negative 1, positive negative 6, positive negative 2, positive negative 3, positive negative 4. My Q, factors of 6, would be positive negative 6, positive negative 1, positive negative 3, positive negative 2. Now, if you started writing all these out, which would be horrendous, you'd take positive negative 12 divided by 6, which is positive negative 2. Positive negative 12 divided by 1, which would be positive negative 12. Positive negative 12 divided by 3, which would be positive negative 4. Positive negative 12 divided by 3, which, this should have not been 3, that should have been a 2. Sorry about that. So positive negative 12 divided by 2 would be 6. We could have 1/6, we could have 1 over 1, we could have 1/3, 1 over 2, 6 over 6, 6 over 1, etc. What I'm getting at here is when I'm looking at this and trying to decide my actual rational zeros, I want to consider 6 integer values because we're dividing by 1, thirds, and halves. We don't need to worry about fifths, quarters, or anything like that. So my actual rational zeros are using this list and my graph. So here I have the graph of 6x to the fourth minus 7x cubed, etc. Now I've changed my window settings because everything's so close to the x-axis or to the y-axis. Looks like maybe maybe negative 1/2, negative 1/3, maybe positive 1.5, which is 3 halves, which 3 halves is in the list. Okay, maybe thirds, but it looks like this one's maybe 3 halves and negative 1/3. Okay, so those are going to be my guesses at this stage, but I've got to try them. I might try negative 1/6. I could try negative 1/3. Okay, 1.5 is 3 halves, so I might try that. So those are going to be my possibilities. So at that point, I'm going to take my calculator and I'm going to start using some other functions in order to determine what values actually work. So what I've done here is I'm going to my graph and I'm going to use the trace feature, and I know that it looks like it crosses at, we said about 1.5, so I'm trying 3 halves, which is in my list. 3 halves does give me 0, so that's one of them. There's one of my actual rational zeros. Then it looks like maybe negative 1/3 or negative 1/2, so I'm going to guess negative 1/3. I'm filling that in, I get 0, so there's a second rational zero. Now I don't see any others on my graph. You'll notice it crosses vertically pretty much without any hesitation through both of those. So I'm going to guess they're both multiplicity 1. So that's 2 of the 4 possible solutions. The thing is, it's a positive 6x to the fourth, so it should be, in behavior should be up on both ends. So my guess is that either something's way off the screen or 2 of these are imaginary. And if they're imaginary, I'm not going to find them in this rational zeros list. So what we're going to do is we're going to use our synthetic division to help us out. So we've determined from our graphing calculator that the actual rational zeros are 3/2 because it gave us 0 and -1/3. And remember, when we're looking at that calculator, we should only look at ones that are in that list. Okay? Otherwise, it's a waste of our time. So at this point, I'm going to use synthetic division to help divide out these solutions to get down to the ones that might be imaginary. So I'm going to take either one of these. It does not matter which one. I'm going to put in my 6, -7, 21x squared minus 28x minus 12. I'm going to put one of the values, either one, out front. So I'm just going to go with the 3/2. Do not let the fraction scare you. It's not scary at all. I'm going to drop that 6. Whoop! Did it again. I'm going to take 3/2 times 6. Now off the side I'll do this once. 3/2 times 6 is 18/2. 18/2 is 9. Okay, so basically I multiply the top by 3 and then I divide it by 2. So I'm going to add those, I get 2. Multiply, I get 6/2 or 3. Add, I get 24. Multiply, I get 72/2, which is 36. Add, I get 8. Multiply, I get 24/2, which thankfully is 12. Add, I get 0. So check. Indeed, it came out one of the zeros. So now I went from an x cubed, or excuse me, x to the fourth, down to an x cubed. An x cubed, I still don't have a quadratic equation for cubics. It doesn't work. So I'm going to divide out again. This time with x equal -1/3. Okay? It's like factoring a number and then taking another number out of it and then another number out of it. We only work with what's left over. So I'm going to drop that 6. Woo! I'm going to multiply. So that'd be -6/3, which is -2. I'm going to add, that's 0. I'm going to multiply, 0, add 24. I'm going to multiply, that's -24/3, which is -8. I'm going to add, that's 0, multiply, add, I get 0, check. We've got it. Now, here's the key. We're down to, we went from a 6x cubed down to a 6x squared. So we have 6x squared plus 24 equals 0. Since we don't have a b term for a quadratic, we can simply slide the 24 over and divide by 6. So I'm going to make this a little smaller so I can have some room to write. Okay, and I'm going to say 6x squared equals -24. So x squared equals -4 when I divide. I'm going to take the square root of both sides to take x as positive negative, radical -4. So x is equal to plus or minus 2i, imaginary. Okay? So, there is my synthetic division to find the others. Okay? So finally, I'm going to find my linear factors. Now, to recap, we use the P over Q in our graphs to help us get the actual rational zeros. Then we use synthetic division, quadratic formula, whatever, to finish up. And in this case, we found the two others were imaginary. They could have been irrational, like square root of 2 or something like that. You would have not gotten those out of the possible rational zeros P over Q list. So these are my 4 zeros. 2 of them real, 2 of them complex or imaginary. So now I'm going to turn those into factors. Now, it may actually be easier to take the x equal 2i and x equal -2i first. So if I take the x equal -2i and I slide the -2i to the other side, it becomes x plus 2i as a factor. If I move the 2i to the other side, it becomes x minus 2i as a factor. Now, what's unique about these first two is that I don't want x minus 3 halves as a factor. So the first thing I'm going to do is I'm going to double both sides to give me 2x equals 3. Then I'm going to move the 3 to the other side to make that 2x minus 3. If you need to, stop that video and check to see that if you set that equal to 0, you would indeed get x equals 3 halves. That's preferred at this level especially rather than x minus 3 halves. We wouldn't factor in that case. Similarly, we're going to triple both sides on this one to have 3x equal negative 1. So add the 1, we'll have 3x plus 1. If you check that, you will indeed get x equal negative 1/3. So, ladies and gentlemen, this area right in here, all of that is the linear factorization for the polynomial that was given g of x. And I guarantee if you distribute those two, get a quadratic, and then multiply that by the third one, and then that by the fourth one, you would indeed get the original. You can trust me. That is basically follows an example of for the first one, g of x, and kind of gives you a support of all the different steps that I've outlined there.